Okay then, on the middle page, what have we got? The Excel tutorial from last week was there, the intro. But if you've not worked through it, please work through it. There are some very useful tools in there that you are going to need for all three tutorials. We've got today's one. I'll load this one up for you to access when we're doing the tutorial today. But after the tutorial, I'll probably hide that one and then give you this one here, which has got all the step-by-step if you weren't in the class at all, just so you don't miss anything out if you weren't here. Mainly for those on the recording, not for you guys, but you know what I mean. Right. So week 3, we had an extra question, didn't we? For those people that did attempt this, thank you very much. There was a small, uh, not a typo, but again, essentially, I'd said go and find it yourself, and then gave you the answer. There's a few people, I don't know who it was, but there's maybe quite a few people actually went and found the result themselves, and they got 110 gigapascals, but I've got 117. Maybe did anyone do that? Get 110? There's quite a few people did, and they're probably absolutely correct because I did say go and find it, and then I then gave it to you, which is bizarre. And I think Dion picked me up on that. Is that right? Did you also find it in Google? Right, and was it 110 though? And that's perfect, right, good. Because I was going through people's results and I'm going, there's an awful lot of people getting 110. And I thought, and if you were one of those people, I do apologise because what I wrote to you in an email was you've got your unit conversions wrong. Actually, you haven't, so I apologise now. It's just where you got the data from because I thought it was 117. Anyway, let's go what the results were. I'll make this available now before I forget, because I will forget. Make this. So this is for week 3. File notes, answers to questions. I'll make that available. So you can go through it in your own time, but we actually have it already loaded up. So we write down, again, good practice to write down all your variables. We've got Parsons ratio, 0.33. Is that for the copper? Yep, that's for the copper. We've got the diameter, 40 millimeters, the length, 800 millimeters, and the E value, 117 gigapascals. Well, that's what I got. Other people got 110. Doesn't matter where you get it from. Just write down your starting off thing. So for those people that I said you converted it wrong, no, my mistake. Nonetheless, you start off with the data, and you also wrote where you got it from as well. If you're doing an online exam or something, you'd write down where you got the data from. In a normal exam or a class test, it would be given to you. So hence why I made people confused. So that's my fault. Anyway, the difference in cross-sectional area, we're told we're looking for 5 millimeters. So that's the A difference. The cross-sectional area cross-sectional area of L unchanged is that. Then the diameter of L after it's been changed. Right, so we've got all of that data. Then the cross-sectional area of that after it's changed. So far you can work all of that out, there's nothing missing. Now the tensile strain of the lateral, you can do that. Does making sense? I think most people got this right anyway who attempted it. And I did email people individually. It was last night that I had, but I did do it. Right, so that's there for you. Week 4, What was the question again? I think it was at the end of the lecture, wasn't it? Right, so an awful lot of people have done this one, which is amazing. I like to see that. And the more you participate in these extra tutorials, actually, it means statistically speaking, you got a much better chance of doing better in the exam. So please just get stuck in and do it. An awful lot of people got this absolutely bang on, which is excellent. And about maybe 3 individuals done incredibly well. They got everything almost perfect, apart from, I think, they didn't get the density of concrete. If I asked you to do that, so yeah, but if I run it here, though, what have I said here? A concrete ballast is placed. Calculate the dimensions of the concrete ballast. That will give you a maximum. Yeah, okay. Excluding any elongation of the rod. Now, remember I'd done a big hint last week. I said, look, you're excluding. I use the laser before and unplug myself. Hi, how you doing? You're excluding the elongation of that rod. You might see this exercise again in your class test, sort of like this, and where I won't be saying exclude something, so you'll have to calculate two separate things separately, then you just add them together, show all your workings, you'll get 100%. It's actually that easy, right? So here though, we're saying calculate the dimensions of a concrete ballast that will give it a maximum vertical displacement of 5 millimeters at the top right here. So an awful lot of people got it perfect up until they thought ballast volume, and then using the equation that I think what they did, I never brought my notes with me. How about I just go and download my notes just now, and I'll try and tell you what I think people did. And I'll look for body language just to see if I'm getting the right answer, if I've guessed the right thing. So just again, general teaching schedule, or schedule, sorry. In that page, come down to the bottom, you've got the notes for the entire module. Go in there. So you now know where to find these notes. Please download them, print them out, or handwrite them 100 times, whatever, but get to know this stuff. You will get a copy of this in the mock exam if we do one, and you will get this in the class test as well, printed out. You won't take your one in, I'll give you a fresh one, because you won't be allowed any hand notes on it. So even though it's a closed test or a closed exam, it's not really. I'm giving you most of the I'm giving you all the equations. Just you have to re-manipulate them. So it's not really a closed book because I'm giving you a big part of it. Does that make sense? The old-fashioned closed book exams were purely a memory test. You had to memorize absolutely everything. Here we're not. Right. So what I think people might have done, correct me if I'm wrong, did people take this equation here and move the delta over to where t is, and yep, and then for somehow thought, oh, that'll give you the volume, the area or the volume or something? Because I saw some people writing it almost like the capital A, even though that should have been delta. I don't know, but it seemed to be that equation there they've done in step 2. So how about we'll just go over how it should have been done? Huh? Right. Week 4. So it's already available for those to look at. Again, if you did participate, you'll have gotten an email from me going through this. So to give the information, length, height, breadth, G, remember G is just emergence of elasticity, but in shear. And then the delta is that 5 millimeters. We know what delta is. That's 5 millimeter displacement at that corner. That's what we're looking for. The solution, step one, I think everyone, one person's not here who, yeah, okay. Hopefully he turns up later on. Apart from that, everybody but one person got step one absolutely bang on. And however, people have done it in different ways. Some people have done it this way, and other people have done it this way here. It doesn't matter which way you do it, as long as you get the correct answer. Sometimes it's helpful if you can see there's more than one way to do something, actually do it twice just to make sure you've got your units and things correct. Can be quite helpful. Right, step two though. Right, density of concrete, I got 2,400 kilograms per cube. I got that from Google, which you were saying, Sean. Sean was saying that's what I said last week. I couldn't remember if I did say that. The acceleration due to gravity. I seem to remember I just said in the class just use 9.81, but here I've used 0.07, and I know Mark Taylor will get you to do to how many decimal places? 5 or 6, yeah, which is amazing until you move, you know, location 4 or 5 centimeters. You know what I mean. Gravity is a geograph is a depends on where you are. Gravity changes due to your rock formation underneath our soil. Anyway, we'll go into that. Not unless you're a flat earther. Right. So force, we got the row of concrete. Row is just like the small lowercase p. Row of concrete times the volume of concrete times the acceleration of gravity. So my notes here 4.8. That means just that sheet that you've got just means equation 4.8 on my sheet. That's all it means. So we have that there, got the acceleration there. So we can just manipulate that to get the volume out because we know what the force is from step one. And now that we've got the volume, we just square root of. Perfect. Easy? So the thing that people might have missed is purely understanding, oh sugar, what's the density of concrete? And I should have made it more clear in the written format. Go to Google and find the density of concrete rather than me just verbally saying it. Maybe that's what was missing. Don't know. Right, so that's all good. Let's go to... Actually, what else can I show you? Let's make this available as well. So this is the exact same thing you just saw. I tend to use Teds rather than Excel, but every so often I'll do things in Excel if it's something quick and easy. Allow it to edit. And when you've got people who are Microsoft Excel users, you tend to find they'll make cells yellow, which is they're saying that's where you're allowed to change the data. So any cells that you see of mine, as any Excel sheets that you'll see of mine or Mark Taylor's or Wojtek's or any of the other lectures that are yellow, that means that's if you change that data, everything else should be correct. Will automatically correct. Right. Yeah. So you can sit and play. You can sit and play with that if you want, and change the force if you knew the force was going to be. Sorry, if you change that to say something more realistic, probably even less than that type thing. Make sense? Perfect. I'll have a look at it, play about with it. And last week's lecture's now on that URL link there. And that's last year's video of the tutorial. You don't need that because the tutorial went very well and everything's in the word for word description. Let's go to week 5 now. Okay, so week 5, what we're going to be doing, we've got, I'll make that available. And I'll put today's lecture in here, so hopefully I'll do that in the next couple of days. But just automatically check yourself. Right, I think I've already got this loaded up. Before we go any further, how about we do the mandatory, where is it, class, check if you're in class thing. Got it here somewhere. I do have it. Mine. Thank you very much. And today's date is the 17th. I'll make it bigger, don't worry. Everyone got it? Can I take it away now? Yeah, cool, thanks. Okay then, mechanics of, yeah, so this is test method 1 we're calling it. We're looking at material variability and sampling of material. And there's a document here, BSEN 408. This is a document you're going to have to download. I've got it in Moodle for you. You're going to have to download it, and you're going to need to read through the procedure for next week. I'm genuinely quite excited for next week. Absolutely genuinely. I don't show it, but I actually am. However, let me explain why. Normally, we would do this lab next week downstairs in the heavy structures. We'll probably actually do it in the room we normally do it in this time, just because of people want to oversee what we're doing. But the concept is though, rather than using say an 85,000 pound bit of equipment, I want to do something that we've made ourselves, and I want you to do all of the work. Because normally speaking, what would happen is a technician would do everything. They'd set it all up, they'd press the button, the computer would control absolutely everything, and all you do is watch. And it's quite, not very engaging, I think. We do have other reasons for why we want to do it this way. It also means we can actually then do this sort of test work. Do this sort of test work elsewhere, not just in our lab. So we will get to use, I wonder if I've got it here. There we are. So, oh, brilliant. I know it doesn't look very exciting. It's exciting to me because it's much low tech, very low tech. We're going to use this machine here. We're going to put a sample like this in there. You're going to control the data logger. You're going to control absolutely everything. I'll just be telling you what to do and you'll be doing it. That's the intent anyway. Why am I excited by it? Because quite often we want you guys to be doing the work, not us doing it for you. So it's a bit more engaging. Hopefully this will be a good exercise. And in theory, perhaps next year I would bring the apparatus into this room and we would do it physically in this room and we could do multiple samples, not just 3 of them. We could do a lot more. That's the reason behind why I want to do this. So these are my guinea pigs, make sure that it works. But I'm sure it'll be fine. However though, regardless if we're using old technology or if we're going to be using the state-of-the-art equipment, which you will get a shot of as well, absolutely. Well, I say shot of, you'll see I'll be doing it, but you'll be there. We're following the exact same standard, which is the BSEN 408. Not to bore you to death with this, but why is it important that we do do testing to a standard? Why would it be important? Just somebody shout something out. If I'm going to test this piece of wood today, and then you're going to test another piece of wood in a few weeks' time, but in Israel, why is it important? Like in a different lab is what I mean. Yep, you're removing anything. You're removing all the variables out of the equation as far as possible. Right. So you need to understand. Sorry. Does that work? That worked. Perfect. Okay. So for just now, let's go back 5 steps and look at the raw material itself. Engineering materials are inherently variable. We're not just talking about wood, we're talking about concrete, steel, everything. Um, Steel properties vary depending upon the chemical composition and the methods of manufacture. We've got hot rolled, cold rolled steel, different grades of steel. Concrete properties change depending upon, I'm going to be honest, absolutely everything that's in the concrete, where you get the aggregate from. You know, literally what is the aggregate made out of. The cement's a bit more constant. The water, what water are you using? What's in that water? The curing time, air temperature. Wood properties depending upon the tree species, method of cutting the tree, we'll discuss that, or we will do, the moisture content at which you test the wood, and so forth, and an awful lot more. Variability is an important parameter in defining the quality of civil engineering material. So you've covered most of this last year with Juan. However, we'll be looking at timber more predominantly. Material testings are performed not only to evaluate the certain property but also to ascertain how much variation is in that property occurs within the entire lot. So if you've got a batch of wood and it's all came from one forest, so we've got a project just now. Do you know what? I'm going to do this because it's actually relevant. Mousey mouse. I was nope, 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 nope. Oh, it was all in the emails, wasn't it? It was in the emails, not this. Let me find it for you. Come on, where's the emails? Too many things open at one time. Right, I'll find the email first before I. So we've got a project at the moment. It's actually, there's a non-disclosure we've signed. So I can't tell you too much about the actual project, but I can show you what it is we're building. Because in theory it could be millions of pounds worth of work if it all pans out nicely. We're just doing the research work for it. Sent items. It was pretty sure it was Saturday night. Yeah, there it is. You probably want, yeah. This is parts of it here. Oh, sorry, you can't see that. You can't see any of that, in fact. Sorry. That's so annoying. Um, Without telling you too much about what it is, I can tell you the species is Douglas fir. It's a shelter of some sort, and it's commercial. And it's ungraded timber, at the moment anyway. Okay, I'm conscious that I'm probably losing you here, because um, yeah, I can show you that. Evidently I can't. Oh, this is getting really boring. Sorry. So we're doing various things. We're doing a structure, it become mass produced in the factory, but we're just building the prototypes of it just now and doing all the mathematics for it. However, the problem is they want to use homegrown Douglas fir from a very particular forest. Um, that all sounds very well. We can commercially grade Douglas fir, so there shouldn't be a problem. You would have thought, come on, mousey mouse. There we are. Shouldn't really be a problem. Do you know what? This is starting to get a bit boring. Yeah, it shouldn't really too much of a problem, but however, we actually want to use Douglas fir for other reasons. Douglas fir is very good for weathering, so it won't rot as fast as say Sitka or other materials. I mean, larch is another material we could have used, which will last outdoors. However, we want to know the material properties not just of the average Douglas fir, we want to know the material properties of the Douglas fir from this particular plantation, which is quite a thing. So imagine you're in this project and we're starting to use material from a particular forest and you don't have the big sawmill backing, so you don't have the big machines for doing material grading, but you do have what's called an MTG. I hope I'll get to show you one later on. Right, so we need to know the variability of the forest, the material we've got in that forest. Let's assume the sawmill wants to sell the stack of wood, structural use, in our case for these shelters. In order yep. A measurement of the variability is the standard deviation. You've all seen this before in mathematics, haven't you? Right? So if this is our data here, that's actually a 3-point bending test. You'll be doing a 4-point bending test, which is slightly different. But just assume we've got numbers of samples. There's 22 samples there. We test all their strength in 3 or 4-point bending. Doesn't overly matter for this. That's our group of material. We want to find out the standard deviation of that. So first of all, we find the average. So you add them all up, divide by n. There's your average. Then you want to find the variance. So this is us trying to calculate the standard deviation. And then once we've got the variance worked out, so what that is, you get your average, there's red, and the variance for each one is calculated and then divided by the number of. That's you getting the average variance. You've now got the average variance. So you're taking the average variance and you're the average variance square root, sorry, and you're just dividing it. Sorry, you're then just start again. The average variance squared is what you've got here, but you're then taking the square root of that just to get the standard deviation. Does that make sense? I've done that very badly, and I know I've probably confused everybody, so let's do it very quickly again. You work out your average, that's a singular number, so it's just you add all the blue heights up, divide by n. Once you've done that, you then take the variance for each one here, and you square it, you add them all up, and you divide by n, and you've now got the variance squared, and then all you do is square root that to get the standard deviation. Probably the best thing to do is to actually just try it by hand on an Excel. But there's the written description there, so I just read that myself. So if we've got a stack of wood and the standard deviation is quite a small standard deviation, that means it's all roughly the same. If we've got a stack of wood and the variance is much bigger, that means your pieces of wood are a mile apart from each other. Does that make sense? So when we're buying wood, if we're buying wood, say at C16 grade timber, we want it to all be, the standard deviation to be quite small is what we want. So there's the same thing. The standard deviation of 2.239 versus the standard deviation of 11.14. If you're going to buy wood in a timber mill and they're both stacks the same price, what would you buy it from? You take it from this one here probably, yeah? Bearing in mind the average value is the same, 15.2. So that's a variation. So you would probably be more likely to want to avoid this as much as possible. Right, sampling. So again, we're back to this Douglas fir scenario. When we're sampling that forest, which we will be doing in real life, not you, but Napier will be doing, what we'll be doing is not just cherry picking the best trees. You'll be actually taking that an average sample, and it means that. And it's quite difficult to not allow conscious bias in there. Because quite often we have conscious bias and we do pick, and we want to make sure we don't. So we have to put in systems in place to which you can then make sure you're not having conscious bias. Right. So they must be randomly selected. Now, when we're doing it commercially, I think most of you've met Wojtek. When he's doing this commercially, he's got processes in place that he's not just, there's ways to do it. Right. If a material property is estimated from a set of samples, the relation for the estimated standard deviation becomes the variance and the deviation. Fair enough. Right. Timber structure, yep. So when we're doing our sessions, we'll be doing the sessions in line with the BSEN 408, the standard here. So you're going to download that document. I'll show you what it is in a minute or two. You'll need to read it to understand the test procedure. So there's no point us doing the test today, because you'll need to go home and actually read that standard, or at least read the part in the standard relevant to next week's test. What you're going to want to do is come pre-prepared for your questions, Because when we're doing the test, normally what would happen is you'd stand there and you'd watch. And you used to do 3 of these in front of you all, right, in the big expensive rig. And it is a beautiful rig, but you weren't even putting your hand, you were just essentially just watching it. And for next week, yous will be setting the rig up, yous will be putting the sample in, yous will be doing the manual jack, yous will be taking the data off the data logger, yous will be doing all of that collectively as a class. Hopefully you all participate, be a bit more interesting. However, you'll need to know a few things about the timber. I've not made the samples. Actually, that's maybe not true. I think I don't know what samples Gary's got, but if he's got the ones I gave him last year, I cut up enough for about 4 or 5 years worth. I totally forget until I see the samples again what they're made out of. So we'll need to ascertain a few things, won't we? We'll need to ascertain what is the sample, where's it came from, what species is it, where has it been stored, how is it being stored, what's the what's the there's words that we need to have a look at. So rather than me telling you what the questions you want to ask are, I will show you once we do these slides where to find BSEN 408 and the page number you're going to need to read. So you can then come with questions. When you do ask questions to the technicians that are there, shout it out. Don't just say quietly to them, because I'll guarantee if you want to ask about the conditioning method for the piece of wood, I'll guarantee the whole class wants to know about the conditioning method for the whole piece of wood. There is conditioning recommendations in BSEN 408, but is that relevant to what was actually happened to the sample you'll be testing? You need to report on that. Okay, 2 material properties will be addressed in this test next week. All we'll be doing next week is compression parallel with grain. That's all we'll be doing. Yep. While doing the elastic modulus, usually noted as capital E, and the material strength denoted as lowercase f. So the sample, well, this is actually one of last year's ones, I think. That's not actually. One of 2019 the sample came from. And it'll be this sort of size and shape. Take the following piece of timber, you've got the height, breadth. Well, your height and breadth should be exactly the same, but you're going to measure it 3 times, 1, 2, 3, then 1, 2, 3, and you'll have to identify exactly what the height and breadth are for that section. You'll take the average. Then the length you'll only measure once. We'll be doing the compressive strength parallel to grain. However, you could also do the tensile strength parallel to grain. We won't be doing that next week or in this module. We will be doing the next time we do a test, which will be after Easter, compression perpendicular to grain, but we won't do that next week. And then there's also tensile perpendicular to grain. Again, we won't be doing that in this module, because from what we've been doing testing on, with compression this way, and 4-point bending, you should be able to get everything else calculated from that. But we can discuss that another week. Questions: how many directions of orthogonal to grain are there? What's your thoughts on that? Orthogonal to grain, how many directions are there? It's a trick question. Every orthogonal to grain with timber, if you look at, I'll use the pointer, you look how the grain's grown. If I test, imagine I cut out a simple block there, and I pull it this way, it will be different to how I would get it if I pull the material for the same area this way, as in that way. And it's all dependent upon the cut of the wood. Hence why how we cut wood has an effect or how we cut a log. We got a log of a tree, how we cut that up will have an effect of the direction of growth of the grain. Right. For the strength properties, we will have the following material stiffness. We'll get E value, elastic modulus compression parallel to grain. We won't be doing the tensile, but you could calculate that. Elastic modulus and compression orthogonal to grain, we'll be doing that. So we'll be doing, yeah, we'll get that in a second. And the tensile, we won't be doing that. During the practical sessions, we will only be concentrating on the things in red. So these two and these two we'll be doing, plus the bending, which we'll talk about in a few weeks' time. So the dimensions, again, in this BSEN 408, the cos 15.2, the length should equal 6 times the breadth. Remember, our breadth and our height should be roughly the same. So that length should be 6 times the breadth. This is quite an easy test. This is a genuinely very easy test. When we start applying the load, you'll get a graph, something like this. It may drop off. This one here evidently did. At some point, the load just dropped off a cliff. This one here, it didn't. The load was still there, but it was diminishing, a diminishing load. So all we have to do is to get the maximum F max. And it's going to Microsoft Excel. You've got equals, max, open brackets, a range of cells, close brackets. It gives you the maximum load. And you want to figure out where in the timeline it occurs. Well, we've got an exercise for that to show you how to do that easier. So it's just the highest value. Right. And so again, we'll be testing it compressively this way. It's a bit repetitive. Right, now we're calculating the E value now. To get the E value in compression, what we need is we need to understand a few things. We've already got the F max. Now we need to get an F1 and an F2. And then, of course, the displacement in millimeters for F1 and F2. Where do we take that from? Right, approximately that's what we're talking about here. So we start off with, we take the F max and we divide by 0.1, that's 10%, and we get a node there at 10% of that. Then we get a node at 40% there of that. Actually, looking at my graph's maybe a bit out of scale, but it's only a pictorial, right? So that should be 40% of that. Now, I have used the term approximate. Why would that be? And why have I drawn this linear line? Or I've tried to draw a linear line here. Can anyone remember my first lecture? When we talked about plastic and elastic? We were talking about in the linear elastic range. So what we should find here as we test this, the 40% and 10% should be a linear elastic range. It won't be perfectly linear elastic, it should be pretty good though. And what we'll do is we'll do something in Microsoft Excel, we'll be doing it today actually in the tutorial, and we'll get an equation of that linear straight line. And we'll then work out the goodness of fit to the live data to your straight line, Okay, and that goodness of fit, we sometimes call it, goodness of fit is the technical term for it, but in Excel we call it R squared, the R squared value, and that will have to be better than 1%. It's quite easy to work out, better than 1%, and then you're all good. If it's not better than 1%, it just then means that the curve, or there's something wrong with the data, and you might want to either move the F2 down a little bit or move the F1 up a little bit. But you need to get that linear line for these 2 points to have an R squared value better than 1%. I'll show you how to do it. Sorry, what am I doing here? Yes, sorry. So back on track. I'm probably jumping ahead of myself here. So we've got our 2 points, and it's our goodness of fit is better than 1%. So everything's good. I don't need to move them anymore. So it's roughly 40 and 10%. We've now got our variables, our length multiplied by F2 divided by F1. Length times F2 take away F1, and the area, breadth and height, times W2 take away W1. Okay, that movement. And that will give us our E in compression. Where's the expression come from? So we've seen this before. This is the modulus of elasticity, or in other term, it's the stress-strain relationship. So that stress-strain relationship, E equals stress over strain. And then we can get stress as force over area, and strain is the movement, or delta. So that W, everything okay? Is delta over L. And so when the reason why we do not consider the initial piece of, right, why do we not take that bottom part of the graph there for? You just think about, I've got a piece of wood, why would I not take that bottom part of the graph for? But as I'm just starting to put a load onto it. Yeah, exactly, that's exactly it. Either things aren't cut perfectly in the saw, and it's not 100%, which things never are, right? And things just settle. Yep. So we'll want to ignore that first part. So during the tests, I have wondered, because we will be doing this probably in the lab as currently programmed downstairs, and we do have the big rig, we possibly could just do the tests how we want to do it ourselves first of all. Right, it will be good fun, but we could also try and do, not try, we could also put one of the samples in the big machine as well, just so you can see the difference. But I think doing it ourselves would be a bit more fun. Right, so we'll actually get data like this, and we'll be going through this in our Excel tutorials next week. But for this week's tutorial, we'll be looking at some of the methods we'll be using next week. We'll get data like this, and we'll create a graph from our data. The last time you 7,000 data points you get? That's roughly what you'll be expecting to get. I've got some videos for you to watch. No, I wouldn't bother. I would just come to the tutorial. Now, I'm going to stop. Hold on. Just where we are. We've actually done very well for time again. I think what we do is we stop just now, and we go. Do we go straight to the lab, and do we just do the lab session straight away, or do you want the break and then come back at 11 o'clock for the lab? Just do it straight away. Everyone happy with that? Right, I'll stop the recording now then. Now, I actually think you'll learn better